Hello guys, I'm back. My name is Jeferson Costa. I'm a chemical process engineer with expertise in plant design and be welcome to Jefferson 9 a.m. Usually I do this live session on Saturday, but because I am doing field activities, my schedule is a little bit confused and I'm using this Sunday to share my knowledge with you in order that you can improve your skills in chemical process engineering and plant design. Currently, as you can see, I am not at my home. Usually in my home, I have a bookshelf behind me. Here I am in the hotel, so I depend on the internet in the hotel. I don't have two screens to help me doing this live session, so sorry for this inconvenience. I am following the chat from my cell phone at my left side, and today let's talk how you really will do the design or the selection and calculation of pump to a plant design. So I have in touch with some articles and some papers these days talking about how is the calculation, what the chemical process engineer should consider are about sizing and selection of pumps for plant design. And most of them or all of them was based on hand calculation. And hand calculations is very, very important, but in my point of view, you will not use it too much because we have the process simulation software to save time, and you will see here how to use the Aspen Hysys to get the pump head, how to calculate the NPSH available in the Aspen Hysys, how to do a system curve, and etc. So this is it. I hope you like it, and let's start with the content. But before that, let me know where are you from, because it's very, very important to me to know where are you from. I am from Brazil, a chemical process engineer from Brazil, and I want to know, or it's very, very useful to me to know how far my message reach people around the world. So, uh, okay, now Sorry guys, I just realized that I instead of turn off my video, I turn off my audio. Sorry for that. So I will share with you what was the source, or what I will use to support me to do this live session with you. And let me be a little bit smaller here. Okay. Now I think that we may not any problem. So to support me in this live session, I will use module 2 of Vijay Sarat's selected topics for chemical engineers. If you don't know his book yet, Vijay Sarat is a very nice person that shares his knowledge in the LinkedIn. And he prepared something like a handbook, or he compiled all his papers in just one book in order that you get familiar with hand calculations and fundamentals related to chemical process engineering and plant design. And for this live session, for this class, I will use it as reference because two things. The first one is because when we are doing something new in the Aspen Hysys, I recommend you to try to replicate what already exists, because this way you will be comfortable with the results. You will be able to verify if the results make sense or not. And once you understand the procedure, you can go to new designs, to new process, and have confidence that now you know how to use the tool based on the fundamentals. The second thing is that the model 2 of his book is probably the most complete hand calculations guideline that you'll find related to centrifugal pumps operating envelopes, because here his main tasks, or his main goal is to show to freshers or experienced engineer how to do the system curve and verify the operating points, taking into account that the pump is already installed, is selected, and the control valve is already installed and selected. Everything that he explained here has fundamentals and are possible to do hand calculations. So it's very, very nice. And I will get this drawing as reference to build our classes here. What is important to you understand that in real life, when your boss asks you to do pump sizing selection, you will not receive this kind of drawing to start your work. You will not receive this information, all of this prepared especially to you to do hand calculation. You will not have the pump curve in a table in order that you can build that in a Excel or add that to the Aspen Hysys. So what is my main goal here is to show you what is more close to real life when we are talking about chemical process engineering, plant design, and about pump sizing and selection. In any case, I again strongly recommend you to download his book. You can find it in the Vijay Sarat's slide share in the LinkedIn, in his LinkedIn profile, or you can download that from my In-Process Boosted Telegram channel, in my In-Process Telegram channel, and the link to join In-Process Telegram channel is in the description of this video. And this book is free for use and to share, so share with as many people as possible. You will find a part focused on pump calculation, and I will talk a little bit about that in this live session. And you will find also a part, the second part of this paper is related to control valve calculations, how to do the calculations and what are the assumptions that you must use during the calculations. So based on that, I will start with our process simulation software. and it will be done in Aspen Hysys, and we use this system here. So we have a vessel, and this vessel is connected to a pump, and we need to pump the fluids to another vessel in order that we can transfer the liquid to one point to another. And you can see that it is a schematic. It is a schematic to let the life of the student easier. You will not find this kind of documentation in the real life. I have never seen that, someone giving you this kind of information this way, because we don't develop this kind of documentation in plan design. We have the plot plan, we have the side view or the lateral view, and we have isometrics. These are the main documents when we are talking about location of equipment, design or routing of pipelines, and I will share with you some examples here. But in terms of teaching people, it is easier to represent the system this way. And just to let you familiar with some nomenclature here, we have the LLLL, so it is the low liquid level. So when you are doing calculations for your pump design and based on related to the NPSH available, you will always consider the minimal level, operating level that you will have in your process, or this in fact is the minimal safety level that you have in your system. And because behind it you can have the NPSH available cannot be rated, and you can have cavitation to your pump. So because of that, you must be aware to inform to the automation guy or to the instrumentation team what is the minimal safety level to the system, in order that you do not damage your pump. On the other hand, in the discharge side of your pump, you have the operating level. For instance, here represented by the static head. When the system is not running, it's stopped, probably the level will be at this level here, at this H here. In any case, for this receiving tank, there is a high liquid level consideration. So your pump cannot, the system cannot surpass, cannot be above the HH liquid level. But as it is possible to reach this condition, your pump must be able to deliver the liquid from the lowest level at the suction to the highest level at the discharge. And the difference between the nozzles in the suction and in the discharge is the head of the pump. It can be represented by length, or it can be represented by pressure, and we'll see how to do that in the Aspen Hysys. Moreover, we have information related to the pipings in the system. We have a control valve to control the fluid, and something that's important to you understand is that the head calculation of a pump is based on your center line. When we have our horizontal pump, it's very easy to identify. So you have here elevation pump center line, you have here elevation pump center line, so you need to take that into account. And in terms of calculations, hand calculations, what is most important to us, or what are the main calculations that we do, is related to head of the pump, we do the NPSH of the pump, and we do the power estimation of the pump, or the shaft power for the pump. Here, this is the GPSA electronic data book. You will see that the NPSH available can be calculated in two ways. One of the ways is taking into consideration the pressure and minus vapor pressure. You will use the specific gravity of the fluids and also the velocity at the nozzle of the pump. And be attention about that because you will see how it influences in the Aspen Hysys. And we can use the pressure in the suction of the pump, the vapor pressure also, and specific gravity, and consider the losses that you have in your pipe system at the suction of the pump. And the 2.31 or 2.31 is because it is not in international standards, it is not international units. Okay, it is feet, PSI, so etc. So because of that, we have this equation here. But for just a moment. But for the head calculation, what you use is this equation here. It takes into account the pressure at the discharge of the pump, the suction of the pump, and there is the elevation related to the center line, as we have seen in the schematics that we just did to us. And this picture here you can download from my in-process Telegram channel. I have posted it a long time ago there, and I will repost in order that it's easier to you to download it. Okay, so we need the equations for head, we need the equations for NPSH available, and there is also an equation for pump power, but I will not show to you this equation because it's not the purpose here. But okay, so now let me return here. And before I start with the process simulation in itself, open the Aspen Hysys, let me share with you or let me show you the kind of documentation that you use when your boss asked you, let's do the sizing selection of a new pump to the process. So as I told you, you will not find this kind of schematic. You can do by yourself to let easier to you to understand what you must do, but what kind of documentation you will have will depend on the phase of the project. If we are in the earlier stages, usually we have at least the process flow diagram. It's the responsibility of the process engineer to build that, and we have the plot plan of the project. So an example of plot plan you can see here, and this reference is from Hev Baron presentation, and you can find his full presentation in the slide share also. So some comments here. First, when we are talking about engineering documentation, we always have a stamp, and for sure he removed the stamp only for the purpose of his workshop. And what matters here is that we have a top view of the system. So let me use this here. So you can see that we have the distribution of the equipments in the plot plan. And here at the bottom, it's probably the cooling water system or cooling tower system. And you can see that there are a number of cells here. And let's suppose that we are talking about installing a cooling tower system, and you need to size and select the pump for the new plant or to the bottlenecking of the plant. In your plot plan, you will have the probably location of your pump or systems of pump. And in this case, it's probably close to the cooling tower system, because you want to less pressure drop as possible from your source of liquid and your pump system. So here you have the pump, and you will have a series of equipments that must be cooling down during the process. So let's suppose here it seems we have a batch of heat exchangers. So we have E, so it may be exchanges, heat exchangers. So how you will do the preliminary calculations to define the pump head of your the head of your pump? You will need to get the plot plan. The plot plan is always scaled. So you can see here that you have a graphic scale 1 to 250, and usually it is in millimeters, and of course that it depends on the location where you are doing your plan design. If you are in the US, probably it will be in feet or in inches, okay? And what matters here is that with the plot plan, you will do, at preliminary calculation, you will do a straight line from the pump to the pipe rack, and another straight line from the pipe rack around the equipments that you will cool down, and another straight line to the equipment. So as it is a scaled document, you will be able to calculate, or you will be able to sum up the distance from your pump and the system that you must cool down. In this way, you will have the pipe length for this process. In the same way, if you are talking about cooling, we have the cooling water supply and the cooling water return, and probably it will do the same route. So you will return with the pipings, with the pipings to the cooling tower system. And with this, you have your total length of pipelines in the discharge of your pump. But not only that, you need to evaluate how is the elevation of the pipelines, because when we are talking about fluids, liquid fluids, as much high is the pump needs to pump that, more heads are needed to the pump. So you cannot consider, it depends on the project. You can see if it has a pipe rack. The pipe rack usually is a structure that supports all the pipelines of a project, and it is not in the floor. It is elevated in order that people or equipments or moving parts can movement below the pipe rack. So another document that is very useful, and usually we use during the preliminary stages of the plan design, is the elevation view, and it is also from Hev Baron, so you can download all of these from his slide share. Okay, so look for it in the LinkedIn. And let's see here, what is the differences between the elevation view and the plot plan. The plot plan show you the top view of the equipment, so you can see where is located each one of the equipments, and you can calculate the distance between them or among them. The elevation view is to let easier to you understand what are the elevations of the equipment. Here you cannot see the distance. If one is behind the other, you cannot see how much length you have from a tower from another. For instance, this tower here, it's in the front of this one. You are not able to identify what is the distance. You need the plot plan to do that. But to verify the elevation view, it's easier to you take. Sometimes we have that, sometimes the elevation is written in the own plot plan, and you have here the elevation. So it's I'm not so sure if it's in inches or if it's millimeters, but what matters here, as in the plot plan, it is also a scaled document. It must be scaled to 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 show you how is the configuration of your plant. So you have here the elevations, and you are able to verify and do your sketch as we have in the Vijay Sarat's schematic. What is the elevation that you must consider, what is the size or the length that you must consider, and with that start your calculation to do the pump sizing and selection. And another thing that's interesting, when we talk about pumps, we don't do the design of the pump. Who does the design of the pump is the vendor, is the QSB, the Sundyne, the Grundfos, and etc. They do the design of the pump related to the how is the curve of the impeller, how is the size of the impeller, how is the bearings and etc., how many nozzles, and this is design of the pump, the mechanical design of the pump. What the chemical process engineer does is the sizing, how much fluid, how much head we need to the pump to be installed in the field, and we do the selection because based on the process conditions, we will go to the market and we will look for the best pump to our process. And all of this we'll talk during this live session. Guys, I am not so sure if my chat is how can I say, is working. I haven't seen any comments in the chat yet. Sorry. Why my chat is not okay. I'm not able to follow you in the chat, okay? Sorry for that. But in the end of this live session, I will review all the comments and I will share the questions that you may have during this presentation, okay? Sorry for that. Do live session outside my home. It's very, very tough because I don't have two screens to help me, and this kind of thing happens, okay? But I believe that my microphone is already fixed, right? I already talked a lot, but there was a time that I moved my microphone, but now it's okay, right? Okay, so guys, so help me for this. In my cell phone, the internet, the chat is not working. Okay, let me. Okay, guys, is anyone there? Please help me. Help me to know if you are following the classes, the class. Okay, thanks, Dennis. Thanks. So let me return to the content. So now let's go to the Aspen Hysys. So just to do a quick revision here, when your boss asked you to do the sizing and selection of a pump, you will not wait for a schematic to you start your process, your plan design, because you will not receive that. You will not receive a list of fittings that are installed in the pipeline. If you are doing a system from the scratch in a greenfield project, probably you will start with the plot plan if it's available to you, and you eventually you will have the elevation view of the plot plan. we are talking about an existing plant, or if we are in the 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 stages in more advanced stages of your project, the piping engineer and the piping technicians will have done the isometrics of the system. So this is for orientation. This document is used by the pipe engineer to build the isometrics. The isometrics that shows the fittings, each fittings that installed in your plan design. It shows the route, the specific route that is used to transfer a liquid from a point to another. So in piping isometrics, usually we have a list of materials, we have the quotations also, we have the usually it can be scaled or not, but you will have the codes here. Okay, so we have the curve. So you see that we have a T here, we have something to fix the piping, you have the length from one point to another, and when you need to do more detailed calculation related to the system, oh, I forgot the name now. The system curve, when you need to do more detailed calculation related to system curve, you need to use the isometrics, because here you will see each fittings, as I told you, curves. If we have check valves, there it will be available here. If we have manual valves, it will be available here, control valves also, and etc. So the isometrics is like the radiography or the RX of your pipelines. You will see each millimeter that was installed in the field. And this document is available also from Baron in the slide share. So you can look for his slide share and take this drawing, okay? For my Process Booster members, my training program, I share some documents, real documents with them. But here for public presentation, I prefer to use something that is already available in the internet. So based on that, let's go to the Aspen Hysys finally. And here, as I told you, I will use as reference the Vijay Sarat's schematics. And one thing that we have here is that we have here is a water system. So I already added the water, and it is 100 water according to his description, process description. And I have the information for the atmospheric pressure or barometric pressure, that it is 1.02 bar. And he gives me the information related to the temperature of the system, and he added also the information to the liquid density. And here it's the first point of attention that I would like to share with you. In the hand calculation, you need the liquid density, and it is a value formed by the problem. However, when we are talking about the Aspen Hysys, the Aspen Hysys is based on the fluid package that you select. All the properties of the fluid is calculated by the Aspen Hysys. So to verify properties of your fluids or of a stream in the Aspen Hysys, first I go double click on the stream and I go to properties. And you will see that I have the mass density here, 997.8. And to reach this mass density, I needed to do adjustment in the temperature. And I did that to us have a closer result as possible, as close as possible to Vijay Sarat's hand calculation, okay? So if I use instead of 21.40 Celsius degree, I use 20 as is informed in the problem description. I would have 998.1, and eventually it will not impact too much in the calculations. But just to make sure that we don't have this kind of issue, I prefer to use 21.4, and this way we have the same mass density. And why the same mass density is important, I will tell you that. But before doing that, let me see in the chat. What is the fluid package that I should use to do this process simulation. Guys, interact with me. What is the fluid package that I would choose to do this process simulation? What do you think about it? And while you are responding, let me see who is here. So I have Dennis Gracia, a student from Brazil. Very nice to have you here. Mishra, a student engineer from India. Very nice to have you here. Cool. Thanks for your advice. We already fixed the audio. Bossale, microphone okay. Pavitra, which institute? Pavitra, I am a chemical process engineer with expertise in plant design. You can see a lot of my contents in my web page, jeffersoncosta.com. So you can see what are my credentials here. Okay, I am not a teacher. I am an experienced, a senior engineer that helps young engineers to get skilled in plant design. Okay, Mualin from Indonesia. Nice to meet you, Mr. Mualin. Says now from Algeria. Okay, we can hear you. Mohammed, chemical engineer from India. I have a lot of students from India. Very, very nice. So Avish did a guess, and he told me to use the Peng-Robson. And it's very, very nice, your participation, guys. And Avish, yes, I could use the Peng-Robson, and the Peng-Robson is the most used fluid package when we are talking about hydrocarbons. But in this specific problem, we are not dealing with hydrocarbons, we are dealing with water. And because of that, I didn't use the Peng-Robson. I used the Aspen Hysys fluid package. And I did that because the Aspen Hysys is built based on the water table, saturated water table, and it's closer. The results with the Aspen Hysys for water will be much, much closer than if I use the Peng-Robson. We can do a test here. For instance, let me see, I can add a second fluid package to my process. So I already have one. Let's add the second one, and the second one will be the Peng-Robson. The fluid package always must be associated with a component list, and I can have more than one component list in my process simulation. So if I'm doing the cooling of the system with water and I am processing hydrocarbons, I can have a component list with water and another component list with hydrocarbons. And let's go back to our process simulation. And I am able to switch from fluid package in my process simulation, going to fluid package, and here basis 1 is the Aspen Hysys. And if I change to base 2, I will use the Peng-Robson. So just to revise, let's see here, I have mass density 997.8. And what happens if I change to Peng-Robson? And guys, I didn't do this verification earlier. Let's see what if it happens. Anything, there is some information that changes here. So what I have here is that the mass density is not more 997.8, it's now 10 or 1010 kilograms per hour. So of course that it will lead to different results in your process simulation. And just another verification, let's see if I change it to 20 Celsius degree, what will happen? We didn't get the 997.8. So instead of using the Peng-Robson, I will keep with my Aspen Steam fluid package because I will have more accurate results in my process. Okay, it will lead to differences in the pump head, and because of the pump head, you can have differences in the power calculation, power consumption calculation, and moreover, you can have differences in the NPSH available. So if you are talking about water, the best fluid package to be used is the Aspen Steam. You can compare, take a book with the steam table and use the Aspen Steam and verify if the results match or not. You will, I am sure that it will match the result from the Aspen Steam and the steam tables that you get from Paris handbook, for instance. So this is the first point. Another information that I didn't fill it here yet is related to the flow, and I didn't do that because I want to explain you something. From the announcement from the process description, we have a flow rate required to be maintained is 189.2 cubic meters per hour. And here it's another thing that you must be aware when you are doing your process simulation. In the Aspen Hysys, we have three kinds of flow or volume flow in the Aspen Hysys. I get this from a post that I did in my process Telegram channel also. Okay, so you can search there for more comments. The first one is talking about liquid volume flow. You have the actual liquid volume flow. So what is the actual liquid volume flow? The calculations related to the flow is based on the mass density at the current pressure and temperature. So if I am doing a process, if my process is 20 Celsius degree, in our case 21.4, and it is 1.02 bar, the Aspen Hysys will get those information related to mass density and will calculate the volume. However, there is also the liquid volume at standard conditions. In this case, the Aspen Hysys always uses mass density at 1 atm and 60 Fahrenheit. And I am 60 Fahrenheit. Here in Brazil we use international standards, international units. Okay, so usually I am more familiar with Celsius degrees. So let's just verify. So it means that the calculation for mass density is based on 16.6 Celsius degree. It means that if you are running your process at 85 Celsius degree or 60 Celsius degree, the mass density of your system is different from the mass density considered by the Aspen Hysys if you inform the liquid volume at standard conditions. And there is a less liquid volume flow consideration by the Aspen Hysys is that the standard ideal. What is the standard ideal? It uses the mass density at 1 atm and 60 Fahrenheit as we have in the liquid volume standard, but only if we are talking about if the components are liquid, so as we have in water, and uses or mass density at 60 Fahrenheit and saturation pressure, okay? Or GPSA mass density if a component is not liquid at 1 atm and 60 Fahrenheit. So it is very, very important to you understand that, because in many cases what I see students doing or people doing is that I need 189.2 cubic meters per hour. So what I will do in my Aspen Hysys, I will see here standard ideal liquid volume 189.2 cubic meters per hour. It's wrong. It's not. It's wrong. It's fundamentally per fundamental. It's wrong, and it can lead to a lot of deviation if at the 15 Celsius degree and at your operation point there is a big change in the mass density of your fluid. And it is, if we talk about hydrocarbons, it can be much worse, because the density varies more when we according to temperature than when we are talking about liquid, about the water, okay? So what is the correct way to do here in this exercise? Instead of adding the information standard ideal liquid volume flow, what I will do is get the liquid density. That's why it was so important to me to inform the correct, add the correct information to my process simulation, and I will multiply that by the actual volume flow, because what is when we go to the field and adjust the flow to 20 cubic meters, we are talking about the actual volume flow. We are never talking about the standard ideal. So in many calculations, it's more reliable to use the mass flow, because mass flow doesn't change with temperature changing, with the pressure changing. Okay, so what I will do right now is do the multiplication. Let me see here. Okay, so I have 189.2 multiplied by 997.8. So multiplying that, I have 188,783.76 kilometers per hour. So this is what I should consider for my process simulation. You can see that it is very close to the, okay, let's see. So you can see that it's very close to the standard ideal liquid volume, but it could not be the same, okay? So be aware of that. And just to, in terms of to let my life easier, no, I don't need to change on it right now. So, okay, based on that, we specified pressure, temperature, composition, flow or mass flow or amount of flow. Now our simulation is converted. So our stream is converted, and instead of being blue light, now it's dark. Sorry. Blue light now is light blue or blue light. Now it's dark blue. Okay, and now let's return to our schematic. Something that is interesting in the Aspen Hysys is that when we add a vessel in the Aspen Hysys, it doesn't take into account the weight of the liquids to calculate the pressure at the discharge or at the outlet of the vessel. Let's take a look on that. Oh. Avish, don't be ashamed, okay? You are here to learn about how we do this in the real life. So if you have questions, if we participate, guys, don't be shamed about the answers that you don't know if it's wrong or right. The important thing is to participate, okay? Don't worry about that, because I am here to help you to be more skilled in chemical process engineering in plant design. So now, okay, so here let me show you if we have, let me add a tank. Okay, let me add a tank and let me add a pipe, and you will see how some of tips that we use when we are doing plant design. So here I have the tank. As you can see in the, I have only the low liquid level. I have no information of diameter or the total length or nothing like that. But I will connect my stream 1, is already defined, and VAP 1 and leak 1, just to let me do the... Okay, so this is converted every time that you have something dark colors, you are converting your process simulation, okay? And I am not able to do a pre-sizing of the tank, because the Aspen Hysys requires to do the sizing of a tank. He asks for two phases. He always asks to have a liquid phase and a vapor phase. I will not do that because we are talking about condensate water. At this stage, we will not have any kind of phase, vapor phase. But I can, for instance, I have 10 cubic meters, and let's suppose that it's vertical, so I have, how much is it? 0.25. So here I will have one volume, and here I will 25%. You see that I don't have any kind of changes in my pressure at the liquid 1. There is any changes in my pressure. Let's 100 meters, and I still don't have any changes in the pressure at the bottom of my equipment. And although he did the calculations related to H and also to the diameter. So what I do to consider the length or the H of the liquid when I'm doing calculations for pump systems, I use the pipe segments to simulate my vessel, or to simulate my tank. What I do here, let me just to look more as a tank. I rotate it and I resize it in order that it looks like more as a tank. And instead of connecting to the vessel V100, I will connect to my pipe here. And when we are talking about pipings, it's mandatory to have a energy stream. And you can see that when you have a red highlight in the Aspen Hysys, it tells you that something is missing, okay? So here I have my virtual tank. Let's say that it is a virtual tank. And what are the information that I have from my schematic? Is that the weight of the liquid is 0.25. So I will go here, I will go to ratings, and I will add a pipe segment. And what is the length of this pipe segment? The length is 0.25 meters. In the elevation, as I am talking about a level and I want to know what is the impact at the bottom of the vessel, the change elevation will be minus 0.25. This way, I take in consideration that I start in the level 0 and I verify what is the pressure when I go down the level 0. And the diameter, it's a tank, so I can use, for instance, just enough to compromise the pressure drop calculation. So here I will consider that the outlet diameter is 10 meters and the inlet diameter can be 9.99 meters. Okay, it is carbon steel. The length is very short, so I can let the increments as 5, no problem. And I need to add information to heat transfer. In the process description, there is any references related to the heat leaking to the atmosphere. There is any reference to ambient temperature. It talks about the fluid temperature, not the ambient temperature. So in this case, I will consider that the heat loss is 0, okay? And it will depend on where you are doing your plant design. If you are doing in Canada, it's different than doing in Saudi Arabia, okay? If you are doing in Brazil, but in Rio Grande do Sul, it's different than doing in the Ceará. And it's always because of that. Because of that, I always, when I start a new project, I know the location where is the project. I go to the weatherbase.com and I get information related to the minimum temperature, the minimum average temperature, the average temperature, the highest hot temperature, the average highest hot temperature, in order that you can build a temperature distribution and verify if based on that you need to consider insulation to your pipeline, if you need to consider any kind of special feature that is not supposed to have in one location to another. Okay, but what I want to show here and what is important to our calculations is that now I have the vapor phase with 1.02 as informed in the process description, and in the bottom of my tank I have 1.044. If we go to the calculations, if I'm not wrong, he did that. But I will just build the process, the simulation, the process flow diagram, and we will verify some key calculations that the Vijay Sarats did in his paper. So, okay, the first part, I did it. Now I will consider the elevation from the bottom of my vessel to the center line of my pump. I have two ways to do that. I can use just one pipe segment with 7 meters and consider the elevation changes into meters, or I can use two pipe segments, one for the 2 meters and other for 5 meters. I will use the second case just to let easier to you understand what I'm doing and what is the relevance in the calculations. Okay, so now let's return to a process, and now I will add the first pipe segment, the second pipe segment, and this one will be on the vertical to be easier to me to identify that it is vertical. As I told you, it's totally optional, okay? You don't need to do this way. You can use just one pipe segment and have the same result. But in order to verify the calculations, it is easier this way. As we had in the as we did in the first part, what I will do, you go to rating, add a pipe segment, and now I have in my schematic, I have information of the size of the pipeline. So you can see that it is 8 inches nominal diameter. And the nominal diameter is always related to the outside diameter of the pipeline. Something that is interesting to you understand is that the 80 inches is a nominal diameter. When we are talking about diameters that represents from 12 inches to and below, these do not represent the physical outlet outside diameter. When we are talking about pipings with 14, 16, 20 inches, you can convert straight the nominal diameter to the outside diameter. It's not the case when we are talking about sizes below or equal or below 12 inches. Okay, so let me return here. So what I have here is that I have so the length is 2, and again, as it is going to below, we will consider -2, and of course that the elevation cannot be higher than the pipe length. It can be equal or minus than the pipe length. And the outside diameter, in many cases, we use standard schedule as the reference for piping installation. But it depends on the pressure, operating pressure, the design pressure of the system. And here it is already in inches, so I can use the 8 inches. And you see that the inner diameter is smaller than the nominal diameter. And it is this way because you have the thickness. So the outlet minus the thickness, 2 times the thickness, because you have thickness in the top and in the bottom, you will have the inner diameter. And all the calculations related to the fluid flow is based on the inner diameter, not the outside diameter. You will use the outside diameter when we are talking about heat leaking, but it's not the case in this exercise. So based on heat transfer, it will be always 0. And again, now I have what is the pressure at the bottom of my vessel. Now I have the 2.238 bar. Okay. Now let's add this pipe segment. Same. This one is 5 meters. There is no level change, and we use almost the same information. Okay. Okay. Now to be more detailed in my process simulation, remember that it is a sketch. So from this sketch, I can see that there is an isolation valve, there is a strainer, there is a reducer. I can add that to my process simulation to have a more accurate result. I will not do that, but I will show you how you can do this. In fact, I will only install a manual valve isolation valve, just an isolation valve. Let's see here. So to add fittings instead of pipings in your process simulation, you just need to click on pipe segment, and here I have added pipe in the first part. But here I will add now I will add fittings. So you have a list of fittings that you can use, and if the fittings that you want to use is not available here, you can use user define it, and of course if you have a source of information to define to you the key values. So here, as we are talking about a 8 inches pipe segment, I will consider a butterfly valve, because a butterfly valve is a cheaper manual valve. So usually we use a butterfly valve instead of using a ball valve, or instead of using a gate valve or a globe valve. And as I don't want to regulate anything in the suction of my pump, I will not use a globe valve, because it adds more pressure drop. It is for, in many cases, it is for regulation, not for isolation. So just to add some considerations related to pressure drop in this pipe segment, I'm using this butterfly valve. And another thing is that why I didn't use it, the butterfly valve, in the vertical line instead, and I'm using in the horizontal line. There is a reason for that. I just forgot to add the inner diameter, so you can use, it's a butterfly valve is a full bottle, so I will use the same size inner size. Okay, so inches. Okay, now it's converted. Now it's something very, very important to you understand. In the schematic, the valve is shown in the vertical line. Not necessarily it is installed in the vertical line, because it is a schematic. What it will tell you if this valve is on vertical or on horizontal is the isometrics, is the more reliable document to verify the arrangement of the system after going to the field and verify by your own eyes, okay? Because sometimes when we do plan design, the project documentation are built, but there are some changes in the field, and eventually the documentation, the project documentation is not updated. So if you are in a industrial facility, if you are in a production, in a process that already exists, get the documentation, but always go to the field to verify, to match if everything matches one with another, okay? The same for pipe instrumentation diagram. And here, it's a matter of experience. Imagine this, a butterfly valve is a valve that opens this way. It's closed, we have the tube here. We have the tube here, and in this position it's closed. To open that, you need to change, to turn around the hand, to turn around the valve in order to let the liquids flow to the system, okay? So you need to do this. It's the same principle that we use in ball valves. During commissioning in startup, usually we fill the tanks or the vessels with the isolation valve closed. And now imagine if we have 2 tons of water in your tank, how will you be able to turn around the manual valve? Because there will be much pressure in one side and almost any pressure at the other side. So to prevent that, to let the life of the operator easier, instead of having the acceleration or the gravity working against you, we add that to the horizontal position, because now this way the forces the valve will be much lower, and now to open the valve will be much easier than doing in the vertical line. Okay, eventually to be able to do that, you will need to have a series of engines to use to be able to apply the force that is needed to turn around in the vertical line, in the vertical arrangement. In the horizontal, no, it's by human strength you are able to open and close the isolation valve. Okay, stay aware of that. It's something that you only learns when you go to the field and you have a lot of lessons learned to your life. So now here you find that for free. Let me see if I have any question. No, any question? Hello, Fazut, I'm from Thailand. Okay, guys, let's proceed with our process simulation. Now, based on the scratch, I'm not considering the strainer, I'm not considering the reducer, but you can add that to your process simulation. Okay, let's only add the pump. Let's add the pump, and the pump is here. I have the suction, I have the outlet, and as a rotating equipment, I need to add a source of energy also. So here I did add that, and different from the Vijay Sarat's Model 2 process description, here we are interested to verify if with the system information we'll get the same pump that was used in the process description. Okay, so I will not add at this moment any information related to the pressure ratio, any information related to the delta P, dirty, because in the end of this exercise we will compare with what is available in the paper. Okay, so now interesting thing that I would like to mention is that the adiabatic efficiency can vary a lot depending on the size and depending on the kind of the fluid that the pump is designed. So there is some recommendation that asks for 70% of adiabatic efficiency for the pump as an initial guess. And if you don't have any other reference, of course, that you should use that. But similar projects is the best source of information to you verify the adiabatic efficiency of the pumps. Because I have seen pumps with 45% adiabatic efficiency, for instance, in the air separation units where we need to pump liquid, cryogenic liquids. There is pumps, water pumps that can have 60 to 65 adiabatic efficiency. And what are the impacts of considering adiabatic efficiency higher than it is supposed to be? Is that your power consumption or your duty will be lower. And when we are talking about preliminary calculations in a plant design, the electrical engineer will do the sizing of the cables based on the power consumption that you have calculated. So if you consider that a pump will be 80% adiabatic efficiency, and when we get in the next stage of the pump design, we verify that in fact it will be 55 adiabatic efficiency, the cables that were calculated are lost, and they need to be recalculated for sure, but the price will be higher. So the capex of your project will be higher because instead of being conservative, let's say this way, you were optimistic. And if you do the opposite, for instance, you estimated in 55%, and in the later stages, you verify with the vendor that the adiabatic efficiency is 80%, the calculation for the cable should be verified again, but a cable that is able to conduct 55% is able to conduct 85%. So in general terms, if the project manager don't want to, it's not needed to do big changes, not need to do changes, although you cannot have an oversized cable to the project, but that's another issue. And considering that the calculations will be updated, now the electrical engineer will calculate a smaller cable, and as it is smaller cable, it will lower the price of your capex. The capital expenditure of your project will be lower. So if you are saving money in the next phases, your project manager will be happier if you are increasing capex during the next stages. Okay, so what is the best recommendation? Verify if you have similar projects and go to the data sheet of the pumps similar or from similar suppliers, or if you have the similar pumps from the same supplier, it's better to you to use this kind of information, or eventually when you are doing preliminary calculation, get in touch with the vendor to ask for a budgetary quotation, and with that have this kind of information. Okay, so and guys, everything that I'm teaching you here is what I do in real life, and my only purpose doing videos in YouTube is to help you to understand what is a real life of a chemical process engineer. You will get a lot of books, and all of them is designed to teach you the fundamentals, and of course you must know the fundamentals, but they don't give you this kind of information. What you must really understand to do your job, and when your boss asks you to do something, you know from where to start. Okay, so my only purpose is this. Returning to our sketch, let's add the control valve. So the control valve here. Here I have an observation for you. So I will add the control valve, and I will add the pipe segment. And we need to connect them. And here you can see that I don't have, in this case, it's a schematic, remember about that. I don't have the length from the control valve to the tank, and I don't have the length from the control valve to the discharge nozzle of the pump. If we're talking about isometric, we have this kind of information. But here, makes sense to have the control valve as close as possible to the pump discharge, because it's regulating the flow of the control valve. And because of that, I will considering here that just at the discharge of the pump, I have the control valve, and my length, my 500 length, will be only one pipe segment. As we are talking about uncompressed fluids, we are talking about liquids, it doesn't do too many changes to our process. But if we are talking about gases, if we have a great pressure drop, it will lead to depressurization, and it will change the temperature of the fluid, and the temperature of the fluid impacts the mass density of the fluid, and all the calculations can be very impacted in terms of pressure drop if we use the control valve at the beginning, at the middle, or at the end of your arrangement. Okay, but it's not the case here. So there are some objects in the Aspen Hysys that is possible to change its identification. For instance, I want to add a control valve, so instead of using this standard object, what I will do is click with the right button of my mouse and choose change icon. And now let's add something more similar to control valves. Okay, so this way I have the control valve. In terms of calculation, it didn't change anything. Okay, it's only a matter of representation. I will not add information to pressure drop right now. Let's add the pipe segment. And pipe segment, once you know how to do the first, you know how to do every one, okay? So in this case, we have 6 inches pipe segment, and I don't have change elevation here. You can see it's straight. It doesn't talk about any pipe change, although I have here 1 meter. So, but I will not consider that in the straight line. I will add a pipe segment just to represent this in my process simulation. So, okay. Let's do the same. Now we have 6 inches. The heat loss will be 0 also. And there is something that I must talk to you here. Before doing that, now to this point, I will consider the pressure drop in the valve the same pressure drop that I have informed by the design conditions in this paper. So the pressure drop in this paper, if I'm not wrong, is 42 psi. Let me see here. Yeah, 53 psi, but with the conversions, okay, I will use 52. And guys, when I finish this process, all this, I will go back to the paper to us verify the results, okay? And as I told you, you can download the full book in my Telegram channel or in the Vijay Sarat slide share. Okay. Now let's add a pipe segment. No, I will here. What I will do, I will not. Let's do this way. I will not add. Let's let our life easy. So I have 1 meter differences in my pump segment. So what I will do is add this elevation line to my 500 meters pipeline. So here, what I can do is, now I'm talking about an elevation from 0 to above. Because of that, it will be positive and it will be 1 meter. So I start my pipeline at 0 and I finish at 1 meter elevated. Okay, in terms, it could be the same if I added the pipe segment in vertical, and after that here, now I zooming up, so it is here. Okay, the length now is 500 plus 1 meter. Okay, so now, and we will add now the tank as I did in the first tank. As I did in the suction side vessel, I will do the same in the receive tank. Instead of using a vessel that is available in my Aspen Hysys, because that doesn't take into account the age of the fluid, the level of the fluid. I will use a pipe segment, and this pipe segment will have 4 meters length in vertical. So let's do the same here. That it looks like as a vessel. 7 each. We need energy. Energy will be 0. And here we don't have information related to the size of the vessel, but I will add a diameter big enough to have any kind of issue related to the pressure drop. So let's add also. So the length is 2, the elevation is 2, and let's 10 meters. 9.99 meters. Okay. And now my system is almost completed. But I need to define what is the pressure at the discharge of the pump, because what I am interested with when we are talking about piping sizing selection is the head in the pump and the NPSH available in the pump. We'll see that in a few minutes. So I have some ways to, my target here is 1.02. Let me see something. Okay. Let me just rectify something here. We can do that later. So what I have here, let's return here, pump suction conditions, pressure. In the paper, it talks that the vapor pressure in the storage tank is 1.02 bar. Okay, and here in the vessel is not 1.02, is 1.04, because it has there is a manometric pressure here. We will revise that later. Okay, so to adjust the pump discharge in order that I have 1.02 bar, I will add the adjusted. It's a tool that you will use a lot when we are talking about plan design. Okay, instead of doing try error, what is my target? My target is in the, I always start with the target variable. My target is stream 8. So what I want here, I want the pressure, and what I will vary to get the pressure here is the pump discharge, because the pressure drop in the piping will be calculated. The pressure drop to the design case is already fixed, and now I need the pressure at the pump's discharge to reach the desired condition. So here we have 5, and in this way I will adjust the pressure, but it's not mandatory to use the same variable when we are using adjusted. You can use different variables. They just need to have some kind of correlation. I will increase the maximum iteration, and when we are using the adjusted, we always need to do a guess in the variable. So here I will use, for instance, 7. And you can see that the Aspen Hysys did the calculation. Okay, and when we have something highlighted in yellow, there are some kind of warning. We will verify that. And the adjusted is not activated yet. It's on red. And the calculation did a 0.99 bar. It's not that what I want to. I want 1.02. So let's return to this, 1.02, and let's click on start. So it converted. And now instead of having 7, I have 7.024, and here I have the desired pressure. That is the pressure at my HH liquid level. And here, what happens is that the Aspen Hysys will do small pressure drop calculations, and he uses segments to do pressure drop calculations. If Aspen Hysys identifies that the pressure drop in this segment is 10% above the calculation, he gives you this kind of warning. And as I have 500 meters pipe length, it is dividing the segments in around 100 meters. So let's reduce this calculation. Instead of having 100, let's change it for 10 segments. We have the same problem now here. Now we have segments with 10 meters each one, and now we have the pressure drop is okay. The calculations verify that the pressure drop is okay. So it's when we are talking about big lengths, it's something interesting to do this kind of adjustment. So now our process sketch is our process simulation is according to the sketch. I will just verify the pressures and etc. Here, suction vessel gauge pressure. So we have a bar G here of 0.02, and the atmospheric pressure. So summing up with the atmospheric pressure, we have 1.04. So in this case, let me fix this. 1.04. And of course, as I increase pressure, the pressure here will increase also. Okay. And now let's do some verifications. The first thing is that we need the pump to do how can I say this? We finished the process simulation. The process simulation is almost finished. There is some small features that I will show to you how to do. But it's not what we will get to send to the supplier. Now you will not be here, click 2 times and write an email asking for a pressure head of 52 meters and use this information, compile this information in an email to send the vendor supplier. So what we do as chemical process engineers is get the information from the process simulation and transfer that to a specification datasheet or a process datasheet for equipments, in this case pumps. Depending on the software that you are using, it can be automatically, or depending on the sizing of your company and the tools you are using, you need to do that manually. But I will show you to you a template that I share with the students of my training program. But before that, let's verify here what's happening. So in terms of results, I have the pressure head, 59.08. We have the velocity, we have the total power, and we need to inform to the supplier the fluid that we have, the mass flow or the volume flow to the supplier, and the properties of our fluids. And we need to calculate what is the NPSH available. there is an option here in the Aspen Hysys that gives us this calculation. Here, if you go to NPSH, it's already checked. Normally, I'm not so sure if it's checked or not, but you can go here and verify the NPSH available. And the question now is, can I inform this information to the pump supplier? Okay. And the answer right now is no. Is no, and I will tell you why. As I have shown to you in the beginning of this class, the NPSH is calculated based in two equations. It can be calculated considering only the pressure at the suction of the pump and the vapor pressure of the fluid and the losses in the system, or it can consider the pressure in the system and also the velocity in the suction in the nozzle of the pump. Remember that in terms of calculations, what matters for the supplier or to the vendor is the information at the nozzles of the pump. It doesn't matter if your storage vessel is 100 meters away, 5 meters away, since you inform the correct information at the nozzles of the pump. And it is the same for the Aspen Hysys. So what the Aspen Hysys do in this case is doing NPSH calculation based on the velocity in the nozzles. The program doesn't take into account the pipeline. So in early stages of the process, we don't have the nozzle size of the pump. But as a rule, the size of the nozzle of the pump must be equal or lower than the size of the suction pump. And it can be equal and the discharge is the opposite. So considering that we have an 8 inches pipe in the suction of the pump, in fact, here in the sketch, we already have the nozzle of the pump. PJ tells us that we have the sizing of the nozzles at the inlet and also the outlet. So what I will do here to have more reliable information related to the NPSH available calculated by the Aspen Hysys, I will do a double click on the pump. I will go to nozzles and I need to fill the information to NPSH available. What interests to the Aspen Hysys is the nozzle at the inlet. In any case, as we have both, I will add this in the inlet and the outlet. So how much is a 6-inch diameter in this system? Let me see something. We have this pipeline that is 6 inches. So we already have a reference. So what I will do is click 2 times here, and I will not use the outside diameter. As I told you, I will use the inner diameter. So what I have here is 154.1 millimeters. So let's return here. Nozzle at the suction and at the discharge. So when I return to NPSH, it is still information NPS available as 48, almost 49 NPSH. So you need to uncheck this and check again, and he updates the calculation. Okay, so it is the way that you can get a more reliable NPSH available and add this information to the supply. But we can do another verification. The another verification is doing the NPSH available calculation based on the pressure at the suction and the vapor pressure of the system. To do that, we use the spreadsheet. In this, and now we get to the fundamentals, right? That's why it's very, very important to know the fundamentals, and I agree with everyone that says that, but I am not in the team of people that says that you must do everything on hand calculation. I believe that it's very, very important to know the fundamentals, how it looks like, what you must be done, but not necessarily you need to do this hand calculated. So here I have this equation, and what we use this one. What this equation tells us? Tell us that we need to consider the pressure at the suction, at the nozzle suction of the pump, and we need to consider the vapor pressure of the fluid. This is because the units conversion, and we need to divide that by specific gravity to have the NPSH in meters. The losses was already calculated in the just a moment. The losses was already calculated by the Aspen Hysys. I don't need to add that to my calculation. What I need is to consider the pressure at this point. I need to consider the vapor pressure at this point, and I need to consider the mass density at this point. It is what this formula tells us. And you should consider also the pump elevation, but in this case, I will not worry about that. So here, when we get the spreadsheet, you are able to import information to here, and you are able to export information here, and it looks like an Excel spreadsheet in your Aspen Hysys. So I will add the information related to the stream 5 that is at let's just verify. So sorry, it's the stream 4. So I will get information from stream 4. So I want from stream 4, I want the pressure. I want the vapor pressure, and the Aspen Hysys identifies the vapor pressure as the bubble point pressure. So this is the vapor pressure that we are looking for. So I will use the bubble point pressure 1, and I need also the mass density. Mass density. Okay, I have the 3 variables that I need to do the calculation, and I have the identification cells. I go to spreadsheet, and now I will do the calculation of the NPSH available considering only this information and not the velocity, because the Aspen Hysys will do the calculation always based on the velocity in the nozzle. So what I need is the pressure at the suction, that is A1, minus the vapor pressure, A2, divided by the mass density, A3, and I need to convert that to kilopascal, so it is multiplied by this. Oops, something is wrong. Specific gravity. Just a moment. I need to consider the gravity. Okay, so now I have the calculation of the NPSH available at the suction of my pump. And I am able to tell the Aspen Hysys what kind of variable is this. So if I go to variable type, I can tell Aspen Hysys that it is length. Let me see length. Okay, so it gives the units of meters to me, and I am able to identify it, NPSH available. Okay, so the calculations are done. It's pretty similar to what was calculated by the Aspen Hysys. Okay, and I am able also to show this in my screen. So what I will do is click with the right side of my mouse, click on Show Table, and now I am able to add the NPSH available calculated. So with this, you have everything that you need to do a quotation of a new pump to your plan design. You have the flow, you have the process conditions at the inlet of the pump, you have calculated the pressure head, you have the NPSH available, and the only thing that you need now is a document to fill all of this information. In many cases, what we use is a template, and this kind of template is available to the members of my training program. So here you have a cover, you have the execution, check, approval, date, revision, control or index of revision, and here what matters for us as chemical process engineers is inform conditions related to operations. So we have rated capacity. In many cases, this one is the most important ones. We have the design capacity, how much time per day, per hour, per year, and NPSH available. We have here. We have design conditions. What are the design temperature conditions? What are the pressure design conditions? Because remember that here we are talking about operating pressure. But let's suppose that we have a pressure safety valve here at 10 bar G. It's possible to this vessel reach 10 bar G. It's not the operating, but it is for design conditions. So you need to inform the supplier, because eventually the seal of the pump will not be able to handle this much of pressure, and we need to add a pressure valve, a pressure safety valve at the suction of the pump. So all of this is part of plan design. So we have information about the liquids, and the performance is by the supplier, and we have some site data here that is very, very important. This is something very, very important to understand, that if we will add the pump in the field, the requirements for the motor can be different if we install that indoors. And if we have some kind of flammable around the area where the pump will be installed, the requirements for the motor will be different also. So this is related to the IP protection or ingress protection of the motor, and also the electrical area classification. But it is a subject to another meeting. Okay, and we have some other information that is more it's more interesting, or it's more related to mechanical engineer, not necessarily to the process engineer. And depending on the size of the pump, we can have some kind of cooling or heating. There are information here related to utility conditions and etc. And this way, when we add process information to this template, to this specification datasheet. Eventually, the mechanical engineer will add other information, and the electrical engineer will add the other information. You get this and send it to the vendor to have a quotation to the pump that will fit your process. Okay, let me see something here. Guys, I'm talking too much. And now to finish this live session, and I will verify if you have questions. Let's verify some calculations that was hand calculated. So here we have information related to the segment, to the pump suction conditions. We verified that we adjusted our model to get the same liquid density, the vapor pressure or the boiling point we have in our process simulation. It is 0.025 here because we are with 1.24. We have the required NPSH required in the pump. It's a vendor information. We have the discharge head 6.29 here, and in terms of meters, 64 meters. It's slightly different from our calculations. Here we have 59. We have the pipe inside diameter 0.20, 2027. Let's verify here. (2027), the same information. The discharge pipe inlet, we have seen that is 0.154. The roughness of the pipe is 45.2. Let's see how here it's 45.7, but we are able to change that. We can go here. 45.2. Do the same. We can do the same here. Okay, moreover, there is some assumption here. We have the curve of the pump. I need to show you. Let me see something here. Guys, something very, very important here. I considered in our calculations, I considered this as 2 meters level because some reason I did this mistake, and you can see that from our schematic it's 4 meters. It's not 2, it's 4. That's why we have some different here. So let me fix that. Okay, the Aspen Hysys did all the calculations again, and now you can see that the pressure head increased, and it's much closer to the hand calculations. That is 64, if I'm not wrong. 64, now we have 61. Okay. And here, Vijay Sarats tells you how is the hand calculation for suction, discharge, friction losses. There is the Colebrook equation and also the Sweeney-James equation. You can see all of these in this paper, okay? We have the velocity in the suction, 1.63. If we go here, feed velocity is not the same. Okay. This is the performance. If we go to performance, you can see the velocity, liquid velocity at the pipe, and that is not the liquid velocity at the nozzle. Okay, it is in the pipe. And here we have the NPSH available calculated. It is as 1.23 bar. So here we have this is emitter. To have in bar is just one minus another, right? So let's see here, equal A1 minus A2. So we have here the NPSH available in pressure 1.21 or 1.22. We have 1.23, so it's the same. And there is some considerations about the control valve pressure drop, and I will not cover that in this meeting. What I want to share with you now, just to finish this live session, is to show you how you can build the system curve. I think it's the only thing that was left behind, and I have the real pump curve to share with you also. So to build the system curve is a function of the flow that you have in your system. If you increase the flow from the design, the pressure drop will increase and the needs at the pump discharge will increase. If the flow decreases, the pressure drop in the system will decreases, and you can have a smaller pressure in the pump discharge. So in order to verify that, what we can do is add a case analysis. So the case analysis, or case studies, you come here, and I will add a new case, and what will be my variable, and here why to let our life easier, I will change the mass condition that I add here, and I will consider standard ideal only for matter of case study. Okay, so it will not change anything, or it's not supposed to change anything. The results must be the same. But for my case study, it will be easier to me because what I have in terms of curve of the pump is with the the flow in meters. So I will consider the same conditions here. I already have here the curve condition in the Excel. I already did that. It's the same that you have in the paper, but now let's add the system curve. And to do the system curve, I will add the find variables. As I told you, it's the one, and I want the standard ideal volume flow. You already understood what are the differences, and it's my variable, and I want as dependent variable, I have two things. I have the in the spreadsheet, I don't need the spreadsheet. I can get the discharge of my pump. Let me see here. Pressure head. So I want the pressure head of my pump, and I want to verify if the pump that I have, if the curve that I have matches with the curve of the system. It's basically this what we'll do, and if we use nested, we can add the information for start, for the ending. I will not use that. I will use discrete, and I will use 10 steps because I want to match with the same information that I have here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the 0 will be the static head. So I will add 10 formation, and I have 93. Okay, now that I did this, I click on run. Let's see. Okay, converted. And now I go to results, and I have the results here in table, or I have the results in plot. So in terms of Excel, what I will do, I will copy this, Ctrl C, and let's add that to my Excel. Okay, so this is head in terms of meters, right? Because the Hysys give you the pressure head in meters. I can convert that to pressure if I want to. Is just do the opposite that we did in the spreadsheet. So I will not do that to save time. What I will do is get the flow and let's build the insert. Sorry, I get the wrong information here. This. Because here it's converting. So now I will take this. Let me see. Okay. Now let's see if it gets correctly. So we have the pump curve, and now we have also the system curve. And I can so we can see that we have the pump curve matching the system curve around 190 cubic meters. So this pump fits this process because everything we did was based on this. And sorry, Danish, it's because I'm doing some just transferring one thing to another, okay? And we are 2 hours talking about this, and so I am a little bit tired, okay? Sorry for that, okay? So now let me show you the pump curve, real pump curve here. And you can see that the pump curve, when you are selecting a pump, must often to the same pump, you can have different size of impellers. So if we filled the specification data sheet, we asked for a quotation. When the supplier returned to you with a pump curve, ask them to add all the impeller size that are possible, or at least the next bigger and the next smaller, because eventually, if consider this pump here, today I am running my plant. It's not related to the process simulation, okay? It's another project that I use and have this pump. So reconsider that today we are running the process with 12 cubic meters per hour, and I have the head of 20 Celsius meters of cooling column of water. And for any reason, I need to debottleneck my process, and I need to increase the volume flow of my system to 16. If I use the same pump, the head available in this pump will decrease to 25 MCA, for instance. And as I increase the flow, in fact, I am increasing the pressure of the pressure drop of the system, and my point of my system will not be here anymore. Okay, it will be different. So eventually, instead, if I have margin to my pump to change the impellers, I can consider having the same pump by only buying another impeller, and now use this curve here. Of course, that I need to build the system curve. You already see how to do that in Aspen Hysys. So if my pump is, if I select the pump with the biggest impeller, if I need to increase the volume and I need to increase the head, I will not have margin for that, and I will need to buy a totally new pump. So this is the thing that I want you to observe. Try to have a pump that you can have some kind of margin to do some kind of adjustment, and don't lose the pump that you already bought. And so with okay, so we have here the curves according to each size impeller size. So we have here blue is 148 millimeters, 135 millimeters, 109 millimeters. So we have seen that the power increases as we increases the impeller, because now we have more heads, and we have for the same head we have more flow. Sorry, for the semi flow we have more head, and for the semi head the correct is for the semi flow we have the more head. So we are increasing the power needed to run your pump. In the NPSH, this is the required NPSH increases with the increasing flow. So we have here the increment. So we need to verify here. For instance, we have 6 MCA, 6 meters of water column. So as I am NPSH available of 12, no problem. It's not the pump again, but just for reference, it is this kind of thing that you will evaluate in a pump curve. And you have the shaft power also related to the curve. So as I told you, if my pump runs at 12 cubic meters per hour, and I using this one pump, my shaft power is 1.9 kilowatts. And but the more it is the usually the shaft power is not the motor size. The motor's nominal size needs to be higher or equal to the maximal shaft power of your system. Of course, that when we are talking about big project, we never use the same shaft power as the motor size. When we need to comply with API or something like that, you have specific margins to be considered or comply with. Here, in this case, the vendor consider the motor size. The green line is the motor size is 3 CV as the maximum shaft power. Okay, so you can see here the motor size is 3, but for this point of the curve, I will not consume 3 CV, I will consume around 2.5 CV. And finally, we have the pump efficiency. So as I told you, in this pump, for instance, and when we talk about smaller pump, sometimes the suppliers add the pump efficiency already considering the motor efficiency. And at this point, we have around 48% of pump efficiency. So if we use this information and feed this information to the Aspen Hysys, you are able to get this power based on this information of head, of flow, and of efficiency, and verify that everything is talking to each other. Okay, so you get the specification sent to the vendor. The vendor will reply to you with a technical economical proposal, and one of the documentation that must be available to you is the pump curve. The pump curve, you will verify the flow and head. You will verify the NPSH required. You will verify the shaft power needed to your pump, and you will verify the pump efficiency. If you are doing projects in the oil and gas industry, most often you will need to comply with the API 610. There is some requirements to pump sizing and selection. For instance, it's talk about the best efficiency point. You can see that here in this documentation there is no mention to the best efficiency point because it's not following the API 610. And you will find it in the Vijay Sarat's paper. Most often the API recommends that your pump runs or operates between 90 and 110% of your best efficiency point or BEP of your pump curve. So to be able to do that, you need a pump curve that talks to you where is the BEP. And the BEP is the highest efficiency of the pump. Okay, the last thing, and now I promise that is the last thing that I will share with you right now, is related to the technical summary sheet that I have here to share with you and explain some terms that we have here. So in this case, I got it from a supplier, and I have the tag of the pump. Everything that you, every time that you develop documentation in the plan design, you will add some kind of identification to your equipment, for your pipes, for your control valves, manual valves, and etc. And we have an identification here for the pump. We have the model, group, and size. It is related to the manufacturer. Each manufacturer will have a different code for this equipment, and this one is not different. So based on this code, you can go to the internet and look for the catalogs and verify if it matches, if it fits or not to your process. It's the first approximation or the first approach that you can do. In this case, I'm considering 2 pumps, and there is the curve number. I don't have the curve to share with you, but you can look for that. And here it's the important thing you try to understand. When you do the process datasheet specification, we add information for the rated flow. The rated flow is your operating flow. So here I have the rated flow of 9.10 cubic meters per hour. And I have the rated total dynamic head. That is the head of the pump in the operation conditions. And here in this technical summary sheet, we have the best efficiency point. It is the point where the efficiency is the highest. So you can see that this pump was designed for a best efficiency point at 9.4 cubic meters per hour. If we get this as reference, for instance, the green, as we were talking about the green line, I am operating my pump at this point, but the best efficiency point of the pump is around 18 cubic meters per hour. So this is the difference between rated point and nominal flow, or best efficiency point flow. So there is the pump RPM, and it is important if you consider to using speed driver to control the pump curve. If you have a speed driver, you are able to the same impeller have different curves to your pump. So it is an option, instead of changing or shifting the pump impeller, you can use the speed driver. It's very useful if you are talking about a process, a system that you need to control the flow of your pump. If it's a fixed flow, you don't need to worry about that. You can use just the impeller at the best points at the design conditions. Okay, so you have the power at the rated flow. So this power is related to this flow, and we have the power, maximum power end curve, and it is related to the maximum. If we get this as reference, this is related to the end of the curve. Okay, so here, for instance, it is 3 CV, and here it is about 2.9 kilowatts. Driver rated power, so although the maximum power is 3, the motor is 4 kilowatts. We have I forgot about this, minimal circulating flow, so you should not get below this point to do not have any issue related to your pump operations. You have the NPSH available at the rated flow, so 4.4, and we have the required rated flow, or NPSH required at rated flow. So it's required 0.65, we have available 4.4, it's okay. And most often from the required to the available, we have from 0.6 to 0.9 meters of margin. We always need to have a safety margin to make sure that you will not compromise the operations and have cavitation in your pump. You have the rated impeller diameter, so it is the impeller for the design conditions. We have the maximum impeller diameter and the minimum. So if for any reason I will need to increase the flow and increase the head of my pump, I have already have some margin to do that. I can change the impeller, for instance. And I have the shutdown head at actual impeller diameter. So for the rated impeller, if I start my centrifugal pump, and remember guys, all of this that we are talking about is about centrifugal pumps. So if I start my pump with the discharge closed, it goes to the shut-off conditions. And in the shut-off conditions, the maximum head of this pump is 26.6. And the percentage rise to shut-off conditions is 15, almost 16%. We have here suction specific speed. It's some correlations that is related to mechanical design of the pump. Okay, we don't get too much in this, but is some standards 11,000 is a good number. And we have the efficiency of at rated flow 31%. So you can see that it's far away from 70%. It's 31, almost 32%. The impeller enclosed, the material. It's important when we are talking about corrosive materials, abrasive materials, to select the right material for the process, shaft material, and here the flanges, and we have the size of the flanges. You can see that ISO 16 and 150 pounds of pressure rating. Oof. Okay, let me be this class for sure is not for everyone. We are almost 2 hours and 30 minutes, and I have some issues with the audio, sorry for that. I will do a rewatch in the comments, okay? And if you have questions, I will consider some minutes some minutes to talk about it. My voice is not good. What time is it? Okay, in Brazil is 11:30. So what we have here, the company has the software defining how do you define rate of pump. The rate of pump is your design conditions, okay? If I need 189 cubic meters per hour, it is the rated flow that I need to my pump. And at this flow, I need the rated head that we calculated this in this live session. So it is the rated conditions, but the supplier builds a series of pumps and for for standard conditions, and you need to choose a pump from the supplier that is best fits to your process. You must, especially in small pumps, the supplier will not design a specific pump to your needs. You need to go to the market and choose the one that's closer to your needs. The API the API 610 talks about having 110% capacity of your best efficiency point. So in the Vijay Sarat's book, you can see that he recommends between, based on his research and resources, between 70, let me see here, let's take a look here. In the considerations, here in the considerations, the minimal stable conditions flow is the minimal flow below which the pump is not allowed to operate. We have seen here that we have here this flow informed some places. Here, for instance, this is the minimum flow. So, although API 610 recommends that the rated region is located between 80% to 110% of the BEP, the preferred region of flow is between 70 and 120 of BEP. So, your capacity, you need to verify your capacity related to the best efficiency point and not necessarily related to your rated capacity, okay, your rated design. But the API gives some exceptions, and it says that if the supplier guarantees the performance of the curve, you can consider that. And one of the issues related to the not operating at the design conditions, you have the cavitation for sure, but although you don't have cavitation, you can have vibration, and vibration can damage your pump. So guys, I strongly recommend you to read and reread this paper of Vijay Sarat. As I told you, the full book is available in my Telegram channel in process, so you can subscribe. There is the link in the description of this video, or you can go to SlideShare and look for Vijay Sarat. Let me return to. Okay, answer Jeff, one query: how the manufacturer tests our pumps? They don't have the real process condition, so how they generate the pump curve? Usually the pump curves or the pump conditions are tested with water, and there are some kinds of correlations related to the mass density of the fluids. So here I'm not sure if in this paper there is no correlations related to that. Yes, there is no correlations, but that's why you see that the pump head is always the same. The pump head is always the same, but the discharge pressure depends on the fluid mass density. So based on that, you are able to select the pump for your process, okay? And in the specification data sheet, you will inform what are the fluid that you are asking for, the properties of the fluid, viscosity, mass density, vapor pressure, and etc. So if you have any issue related to that, you can confirm with them if they must give you guarantees that it works, okay? So it's some tips that I can give you, Danish. And fantastic, private I belong to. Okay, guys, I am very, very tired. I thought that I would cover this in less time. I was planning to do it in no more than 1 hour, but it is, I think this way, I think that who is here up to this point, that we have covered a lot related to pump sizing, selection, and plant design, with what the chemical process engineer must know to do that in real life. Okay, thanks a lot for being here up to this point. If you liked this live session, Please share with other people. I have a goal of reaching 100,000 subscribers in my YouTube channel. So if it worth to you, please help me to achieve this goal. And you can have much more content if you go to my website, jeffersoncosta.com. You will find links for my YouTube. You are ready. If you are not seeing this live session on YouTube, you will find access to my Telegram channel in process. There are lots of useful information, daily life as a chemical process engineer in plant design there. Link to my LinkedIn. You feel free to ask for connections in LinkedIn. I always consider adding new people to my connections. And if you want to know more about my Aspen Hysys training program, you have also the link. Not only that, in my web page, you can find the link for my blog. So there are some useful articles there and more information about me. And for now, is still available my free training related to plant design for chemical process engineers. So I compiled some videos in order to let you familiar with chemical process engineering and plant design. Do you consider to do rigorous heat exchange design tutorial in Aspen EDR? Who knows, Hanif? Probably yes. Currently, I talk about EDR only in my training program. Okay, so let's see. And every week, I have the Chemical Process Engineer Diary series where I share with you more useful information as in my daily life as a chemical process engineer. So guys, this is it. I hope you like it, and I'll see you soon in the next live session. Bye-bye.